तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today, we will continue with the discussion about distortion in amplifiers. Signal distortion, that is what we mean by. For example, let us say the input signal is something like this. Let us consider a periodic signal like this, and this has to be exactly reproduced. Let us say this is 1 millisecond time period. This is the voltage input. So, this has to be exactly reproduced at the output following the same shape. Right? This should not be in any way distorted. Only thing is it should be amplified, let us say 10 times or 100 times. That is the purpose of the amplifier. If it is a voltage, it is a voltage amplifier. If it is a current, it is a current amplifier. Okay. It could be a transconductance amplifier, okay, or trans resistance amplifier. You know all these types. Now, he said that if the amplifier has a characteristic which is, let us say, V naught versus V I, this is called transfer characteristic. Which is linear, then we can see that the slope delta V naught by delta V I is a constant. It is a constant throughout. This remains a constant. This is what is called as the voltage gain of the amplifier. This slope of this is a constant throughout. It remains constant at all points of time, at all voltages, okay, voltage levels. Then it is a linear network. But this is only possible, okay, theoretically, right. In practice, no amplifier can be that linear as depicted here. Whether it is V naught versus V I or I naught versus I I in the case of current amplifiers, okay, or I naught versus V I in the case of transconductance amplifiers, or V naught versus I I in the case of trans resistance amplifiers, the slope has to be linear. For most of the amplifiers, we would like to make it as linear as possible by designing the circuit appropriately. This is done, as I told you, by what is called biasing. proper operation of the device in the proper region, so that the linearity is as much as possible for as wide a dynamic range. What it means is, it is operable over a large range of voltages, dynamic range. Okay. So, this is the purpose of designing amplifiers, to make it as linear as possible. But the first thing that happens is, in order to bias this, we need what is called as DC bias voltages. So, these bias voltages will limit the amplitude of output ultimately. So, these will be, let us say, plus Vs and minus Vs for dual supply. Why do we need dual supply? So that the voltage can be both negative as well as positive. Okay. And the offset, this is another important thing. If it passes through the origin, there is no offset. If this characteristic goes like this, the gain is the same, it is linear, perfectly linear, but there is said to be an offset voltage. So, this is having the same gain as this, but there is an offset. This offset can be positive or negative. So, V offset is made very close to 0. Why it should be made very close to 0? Because this offset may not be constant with respect to temperature. See, the offset voltage may not be constant with respect to temperature. It might be changing depending upon the time and temperature. This causes what is called as drift in offset voltage. So, this drift in offset voltage results in the signal, low frequency signal appearing such that we cannot distinguish it from the actual signal, time varying signal that we are using. So, this offset causes drift. This drift causes signal to noise ratio in the circuit to become poor. We do not want our amplifier circuit to introduce noise, which appears like signal. We do not know what the signal is, and that signal is varying with respect to time, that we are trying to amplify. Apart from that signal that we want to amplify, the amplifier itself is generating a signal which is getting mixed with our signal, and that is the noise, right. So, the signal to noise ratio, right, becomes poor because of the drift. This is particularly so in very low frequency amplifiers. In high frequency amplifiers, the drift being a low frequency component, we can isolate it using decoupling capacitors. Whereas, in low frequency amplifier, since the signal itself is of low frequency, it mixes with the what is caused by drift and results in signal to noise ratio getting deteriorated within the amplifier. So, this offset has to be necessarily made 0 and kept around 0. So, a design of an amplifier therefore involves making the offset as close to 0 as well as keeping it close to 0 at all times, preventing any drift. So, these amplifiers are called low drift amplifiers. These are specially designed DC amplifiers. Okay. So, please remember that when we are given the task of designing amplifiers, for a specific type of amplifier we have to concentrate on specific aspects of design. When it comes to low frequency amplifiers like biomedical amplifiers etc., we are interested in designing low drift amplifiers. These are called DC amplifiers. So, in that case V offset is an important factor. Okay. Next, this particular thing may be getting limited because of the supply that we are using. It is not going up to this. This is the maximum supply voltage. This is the minimum. In the negative direction, let us say it is minus Vs. This is positive direction, it is plus Vs. Okay, dual supply. Above that, it is not capable of giving, because that is the bias supply voltage itself that is used for the active device biasing. Okay. So, this is called limitation due to saturation. So, if I apply a signal which is having an amplitude greater than this, then output is not going to increase further, it is going to remain constant. So, suppose I apply a sine wave here as the input. This sine wave, as long as it is within this, is going to be reproduced exactly at the output, no problem, okay, as a sine wave. But if this amplitude is exceeded, this amplitude is going to get limited here, chopped off here. So, the output amplitude will be just getting limited. So, this is because up to this input amplitude, output is going to be reproduced exactly proportionately. Thereafter, it is going to remain constant. Again, so is the case with the lower limit. So, this kind of chopping off is due to saturation. This occurs in all amplifiers. Okay. So, if you see anything like chopping off the head of your sine waveform, okay, you can immediately conclude that you are applying a signal which is too large, and therefore, output is getting saturated. So, other type of nonlinearity that we can discuss will be what is called as this is no longer changing abruptly like this. So, the slope is maximum at this point and going on decreasing, delta V naught by delta V I, which is okay, the amplification factor. This is different at different points. This is what happens because of what is called nonlinearity. So, this nonlinearity causes it to keep on decreasing and ultimately go to 0. At saturation, delta V naught by delta V I is 0. That means, it is going from a maximum value to a 0 value. So, this is what happens in practice in most of the amplifiers. The nonlinearities may differ. It may not be exactly this nonlinearity. This is a symmetric nonlinearity. So, this nonlinearity is something that causes us to fix the operating point very carefully at the middle here in this case, so that the dynamic range is maximum. Operating point, because of offset, can shift to this, even then it is amplifying, but the dynamic range gets curtailed. Here on this side it can go only up to this point, on the other side it can go this much. Similarly, if the offset is here, then again the range, dynamic range of the amplifier gets curtailed. So, it is important to fix the operating point properly, and the operating point should be stable. right. So that if the operating point drifts, again the dynamic range for your amplifier gets curtailed in one direction. So, operating point stability is also important in your circuit. So, in the design of amplifier we see to it that the operating point does not drift much. Particularly we bother about this in the case of large signal amplifiers, not small signal. In the case of small signal amplifier, even if there is offset, since the signal itself is going to be very small, it is not going to matter much. So, the amplification factor may be still very high. So, this is what you have to bear in mind. So, distortion comes about because of all these nonlinearities. So, let us therefore see what happens to this kind of signal if it is applied here. This is not going to be retaining the shape exactly here, right. Maybe this portion of it may get chopped off and this portion of it may be amplified properly. So, that is what is called distortion. How to measure distortion is what we are going to discuss today. See, the causes for distortion, these are very clear. This is caused by nonlinearity. I have told you the type of distortion that is caused by frequency dependence of the amplifier gain. That is called magnitude and phase distortion, resulting in distortion of the signal. That is different from the distortion that is occurring because of nonlinearity. So, today we will discuss about nonlinearity distortion. Normally, for testing the amplifiers, it is customary to use sinusoidal signal. Why? Because sinusoidal signal can be sort of a generalized signal which a periodic signal, for example like this, can always be represented as a summation of sinusoids. So, a test of an amplifier is normally done by using sinusoidal signals. If you know how it behaves for sinusoidal signals, you know how it can behave for a periodic signal, or for that matter you can also then conclude how it can behave for a periodic signal. So, all these things you have learnt in your networks course. Let us therefore assume that V I is V p I sin omega t. Omega is the frequency of the signal, V p I is the peak voltage of the input signal. Now, if this is applied as an input to an amplifier, what happens because of nonlinearity? Let us assume that we are discussing a voltage amplifier. Which means that V naught is a function of V I. I told you this is going to be represented as V offset, which is independent of V I, plus K naught into V I plus K 1 into V I squared. I am considering now only nonlinearity due to the square term. The rest of the nonlinearity I am ignoring. This is to illustrate as an example, right. So, this is the amplifier that we are going to discuss. So, if this is the nonlinearity that is present in an amplifier, then what is going to be the amount of distortion? Normally, V naught therefore is going to be equal to V offset. This is independent of input. So, this remains unaltered, plus K naught times V p I sin omega t. So, this is coming out beautifully, K naught into V p I amplifies it. Next, plus K 1 into V I squared. So, that is coming as V p I squared sine squared omega t. That therefore is going to be resulting in some unwanted component. What is it that we will see? We have therefore V naught equal to V offset plus K naught V p I sin omega t, which is a wanted component, plus K 1 V p I squared. Okay. Sin squared omega t can be written as 1 minus cos 2 omega t by 2. So, please note there are two things that are happening. It has now produced a 2 omega component, that is, this harmonic generation occurs. This frequency component was not existing in the original input signal. So, this harmonic generation is something that we have to be careful about. This is causing distortion. The amplitude of this, if it is considerable, is going to cause considerable amount of distortion. It depends upon K 1 relative to K naught, right. So, what is the extent of nonlinearity that is present? So, K 1 V p I squared cos 2 omega t is the second harmonic, okay, divided by 2 is the second harmonic distortion, right. Now, suppose I want to know something about distortion. We know that the RMS value of this is K naught V p I by root 2. The RMS value of the distorted, that is second harmonic, is K 1 V p I squared by 2 root 2. So, percentage distortion equal to, okay, K 1 V p I squared by 2 divided by K naught V p I, okay, into 100. This is going to be the percentage distortion. This is what we wanted, K naught V p I is what we wanted, but in addition we have this distorted term appearing. So, K 1 V p I squared by 2 divided by K naught V p. So, this is an important this thing. The percentage distortion itself depends upon the magnitude of voltage V p I that you are applying. That will always be the case in the magnitude distortion occurring due to nonlinearities here. Now, how do you really get this value? K 1 V p I squared you have to get. It is very easy to get this, you do not have to really see the components of these two independently. This is going to mix with this, it is very difficult to isolate this. Whereas, you can see here that the DC offset originally was V offset, now it is going to be shifted to V offset plus K 1 V p I squared by 2. So, just by measuring the offset voltage without signal and offset voltage with signal, this is always the easiest way of measuring distortion. Offset voltage without signal is simply V offset. Offset voltage with signal is V offset plus K 1 V p I squared by 2. You subtract this, you will get K 1 V p I squared by 2. That means, the operating point shifts because of distortion, right, and the extent of distortion will be measured easily by finding out the extent of shift in the quiescent point or offset voltage. So, this is an easy way of practically measuring any amount of distortion. This may be due to second harmonic here, but it may have K 2 V I cubed, that does not matter. Even K 2 V I cubed, okay, sort of can be sort of giving you certain amount of distortion. Then K 3 Vi to the power 4. All these things will cause certain amount of distortion, and all these distortions can be fairly easily measured by seeing the amount of offset shift. Predominantly, when we go to FET like structures, we have seen that it is a square law nonlinearity, okay, whether it is JFET or MOSFET. Okay. The output current is proportional to square of input voltage, and this kind of distortion is quite common, and second harmonic distortion is good enough measure of the extent of distortion in the signal. Okay. So, please remember this. And when it comes to transistors, bipolar transistors, again it is an exponential nonlinearity. Again there will be the square law, this nonlinearity present in that. This square law nonlinearity is absent only in a differential structure. Okay. There the first nonlinearity is cubic. Okay. Square law is absent, it gets cancelled. Therefore, we will see that arranging these different devices BJT or FET itself will cause us to get rid of certain dominant, okay, nonlinearities. So, this is also part of the design. Okay. In the present day design of integrated circuits, it is seen to it that this arrangement of devices is such that, okay, the major nonlinearities get mutually cancelled. So, once again the percentage distortion is an important measure of an amplifier. It tells us the effectiveness of our design such that this is minimized in a circuit. Now, let us summarize the practical amplifier situation belonging to the 4 amplifier categories. Voltage amplifier that we had just discussed, V naught is equal to V offset plus K naught Vi. This is the important term that we should retain. The rest of the things should be made as close to 0 as possible. V offset, K1, K2 should go towards 0. That is how we are going to design a voltage amplifier. That means, the operating point of the voltage amplifier should be done in such a way that V offset is 0 and K1 and K2 go towards 0. Next, how to design a current amplifier. I naught is going to be I offset. This is what is important, right. In the case of a current amplifier, there can exist an output current which is independent of the input current. Okay. I offset plus K naught II plus, this is what is important, okay, linear term. These are the nonlinear terms which should be made as close to 0 as possible. K1 and K2 should go towards 0. That means, something that is going to be defined as current amplifier should inherently have, if possible, K1 and K2 very small. Okay. There is no point in therefore using this kind of characteristics for designing this kind of amplifier. Okay. You must have this K1, K2 basically inherently small for this type of amplifier. Okay. Such a configuration you should select, or such a nonlinearity should be present in the active device. The transconductance type amplifier, this is becoming quite popular these days in IC designs. I naught is equal to I offset plus G naught into Vi, linear term, and then G1 into Vi squared, G2 into Vi cubed, etc. Okay. Your transistor amplifier can be put under this category, by BJT or FET can be put under this category, okay, of transconductance amplifier. Trans resistance amplifier, V naught is equal to V offset plus R naught II plus R1 II squared plus R2 II cubed. Not yet been able to find out a device which is well suited for this kind of amplifier, right. Whereas this, the BJT and FET can very well do the design. Here using BJTs we can still obtain something which is called a current amplifier. Okay. Once again here this can be designed using a FET. Okay. So, the essence of the design therefore is to bias these active devices. Using DC supplies. So as to fix the operating point in a region with the best linearity possible. Okay. So, the next few lectures will be devoted especially to take examples of various devices like bipolar transistors, field effect transistors, single transistors, pairs, okay, combination of these transistors etc. to achieve this purpose. Okay. So, the basic idea is ultimately we should achieve one of the four category of amplifiers with best linearity possible, with minimum amount of offset voltage, maximum bandwidth possible. Okay. This is the idea of a design. So, we will now consider the basic elements which can be used for this purpose. So, the elements that were being used were tubes earlier, electron tubes. These are all replaced now by semiconductor devices. Okay. Like bipolar junction transistor, popularly called BJT. There are two types in this. One is called PNP, another is called NPN. Next, we have what are called as field effect transistors. These are popularly called FETs. There are two types in this. This is called junction field effect transistor. Other one is called metal oxide semiconductor field effect transistor. So, J means junction, okay, J, and metal oxide semiconductor, which is called MOSFET. In these, in turn, we have two types. So, we have JFET two types, N channel and P channel. This JFET, because of the mode of operation of this, is called depletion type. Okay. And therefore, in MOSFETs we have two categories which are basically based on again the mode of operation. N channel, P channel, and then we have two categories under this. This is called enhancement type. This is peculiar to only MOSFET, and this is called depletion type. Similar thing, we have enhancement type of P channel and we have depletion type. So, you can see now the variety of active devices available in semiconductor. So, basically these many devices are available for you to do the design of amplifiers. So, we have to only understand the characteristic of this, the input and output characteristic. We do not want to really bother about how these characteristics get obtained. This is the area of a devices course. We know that these are the various devices available and these have this kind of input output characteristics. So, we will understand in our further discussions about the operation, the biasing, the characteristic of all these variety of devices that are available. So, we are now going to get introduced to these active devices which are working for us to make the amplifier design a success. So, let us therefore be first introduced to an important active device, that is a PNP, bipolar junction transistor. So, I have now taken PNP. Now, only qualitatively we will now understand an important function in BJT, that is called transistor action. How to make it active? So, this is important. PNP transistor built like this, let us say, is comprising two junctions. Compare it with what we discussed already in a diode. It comprised one junction, one PN junction, and we have understood its characteristic. It is exponentially related, that is current and voltages are exponentially related. So, here we have two such junctions, but it is not just equivalent to two diodes in series. This junction is very close to this junction. This is important in a transistor. In order to make a good transistor, I must have this junction very close to this junction. Now, what happens because of this? This junction, which is called emitter base junction, this junction is called emitter base junction. This is normally forward biased. For transistor action, this emitter base junction is normally forward biased, which means this is P is made positive and N is made negative. The moment a junction is formed, you know that there is what is called a depletion layer, which is devoid of all mobile charge carriers, electrons or holes. This layer is called depletion layer. This we had talked about again in diode. The barrier, there is a barrier, potential barrier, okay, which is of the order of 0.5 to 0.7 volts in the case of silicon. Okay. That is why our diode starts conducting only after that cut in voltage of about 0.5 to 0.7 volts. So, this potential hill is there for the majority carriers. In this case, the majority carriers are holes on p side, n side they are electrons. So, what is done in a transistor is the total current normally is made up of current flow due to both holes as well as electrons. In order that transistor action is good, I want to make this total current equal to mostly due to majority carriers in this, right. So, this particular region is therefore made heavily doped. Okay. So, this is really speaking P plus it is called, that means it is heavily doped, and therefore, the current here is going to be primarily made up of majority carriers that are holes, right. So, this IE is predominantly governed by hole current in this region. Okay. So, these holes which are going this way to constitute the current, because it is forward biased, okay, these holes will be moving towards this, electrons will be moving towards this easily. Okay. So, because the barrier height is reduced by forward biasing. Okay. So, a copious amount of current can flow because this junction is forward biased. That means, injection of majority carriers will occur from emitter, that is why it is called emitter. Okay. This can now emit a large number of majority carriers from this point to this side. So, we call this terminal as emitter. So, the design is done in such a manner that the total current is primarily made out of majority carriers here. So, once these holes which are constituting primarily the current get injected onto this side, imagine them here, these holes in this region are minority carriers. So, they are likely to join up with electrons, they are going to be wasted. We do not want this to happen in a transistor. So, what do? We make this region as thin as possible, that is the construction of a transistor should be such that this region should be made P plus and this region should be made as thin as possible. Therefore, we do not lose any of these injected carriers in this base region. This region is called the base region. So, after they come over here without getting lost, without recombining, this is called recombination factor. This recombination factor should be kept close to 1. Okay. So, nothing is lost in this region. So, this injected holes will entirely come to this junction, and here this junction is reverse biased. Why is that reverse biased? This reverse bias is going to cause this potential hill as far as these majority carriers from this side is concerned, to increase. So, these majority carriers here cannot flow this way, but the minority carriers here can now easily come to this side, but these minority carriers now coming to this side are holes which are also injected from this side. So, most of these holes here find an easy path for this to get collected here. So, this region is called collector. So, this is called collector, this is called emitter. So, what is the aim of transistor action? Transistor action is to make as many of the holes as possible on the emitter side to constitute the total current. That is done by making the emitter region heavily doped. Okay. Then force most of these holes to come over here without recombining. That is done by making the base very thin. Then collecting almost all the holes here, that is done by reverse biasing this junction. So, this potential hill is not a hill at all, it is an aiding field for these injected carriers. So, most of them get collected here. So, the transistor action lies in forward biasing emitter base junction, reverse biasing collector base junction, such as to make I c equal to I e. That means, if it is not equal, that factor by which it is not equal is called alpha. Okay. This alpha should be very close to 1. That is a good transistor, and this much should be sufficient for us for using this in its characteristic. Now, as far as the input is concerned, please remember the input emitter base junction voltage and emitter current, these are going to be related in the same fashion. I e is equal to I e naught exponent V b e by V t. This eta factor can also be there. The same relationship that we had used for the diode, because that is forward biased. Emitter base junction is forward biased, and the emitter current therefore is going to be I e naught. This is the reverse saturation current to exponent V b e by eta V t minus 1. Okay. So, this is something that we already know about, exponential, and I c is equal to alpha times I e plus, strictly speaking, this is reverse biased. Okay. If this is totally reverse biased, then there will be a reverse bias current flowing through this, which corresponds to I c naught, which is the reverse saturation current of that particular junction. So, please remember, when a junction is reverse biased, if V b is reverse biased, for example, there would have been I e naught flowing, right. So, same way there will be a reverse bias junction here, and therefore, there is this I c naught flowing in addition to what has been injected from the emitter. So, if you understand these two equations, okay, it should be sufficient for us to really use them in most of our design. So, this is valid whether the transistor is PNP or NPN. It does not make any difference. In the case of NPN transistor, this will be N, this will be P, this will be N, and therefore, this is minus, this is plus, this is minus, this is plus, okay, and then this will be forward bias, that will be reverse bias again. Okay. Only the current directions will be, actual direction of the current will be different. They will be this way, and this way. Okay. So, that is the only difference, okay, in the case of an NPN transistor. So, let us put down that on this side. So, instead of this going in, these are the actual directions of the current. As against this, here it will go opposite there. So, the biasing of the transistor, in order to make it work in the active region, is what is important. So, if we understand this, then we have got what is called as a current source, which is totally independent of the voltage that is applied here. The reverse bias is not determining what the value of the current should be. That current is totally determined by emitter base voltage that you are applying here, and IE is going to be fixed by emitter base voltage at the input, and this IE is now flowing at the output, and you can connect it to any load. Okay. So, this is a current controlled current source. If I have 1 ampere here, this will be 1 ampere. Okay. This 1 ampere is flowing into almost a short circuit, and this 1 ampere can flow into any load. So, you have therefore forced an output current which is dependent upon an input current. So, current controlled current source. So, you can therefore see that the emitter base junction voltage, which is the input voltage, and input current, they are related exponentially. So, that is the nonlinearity. Okay. Emitter base voltage and input current are related exponentially. Output current and input current are related linearly. This is absolutely linear. This linearity is valid over a wide variation in current. Okay. So, this is a great advantage associated with this device, which is a bipolar junction transistor device. So, the current relationship is absolutely linear. This is important. So, basically this is a current amplifier. In the next class, we will get introduced to the field effect transistors, how to have transistor action in field effect transistors, just like this, how to make them work in a region where they can give amplification. So, if you now reverse bias this and reverse bias this, both the junctions will be off. That is called cut off region. This is reverse bias, this diode is reverse bias, this diode also is reverse bias. The entire thing is an open circuit. So, this is called cut off region. Transistor is said to be cut off. This is the region in which transistor is active, where one junction is forward bias, the other junction is reverse bias, the transistor is said to be active. Okay. Both junctions reverse biased, the transistor is cut off, it is open, right. It is equivalent to open circuit here and open circuit here, right. Now, collector base junction forward biased, emitter base junction reverse biased. This is called inverse mode of operation. You are not supposed to operate a normal transistor this way, because we have designed this transistor with this junction heavily doped. This is not so heavily doped. Okay. So, its efficiency is poor. Okay. So, its alpha is going to be not so close to 1 as this one is. So, inverse mode of operation collector base junction forward biased, emitter base junction reverse biased. Please remember that this is also an active region, okay, of operation, but alpha is not so close to 1. So, this mode of operation is not normally used. Then both junctions forward bias, this junction forward bias, this junction also is forward bias. Okay. That means both junctions are short circuits. Okay. So, the entire transistor is a short circuit, or transistor is said to be in saturation. Both junctions forward biased. Transistor in saturation.